Hi, and today's lecture is going to be the final lecture regarding infinite impulse response or IIR filter design. This lecture is focused more on examples on how we attempt to solve problems to do IIR filter design in particular. Just recapping that in order to design an IIR filter, we need to start with some analog prototype in terms of the Laplace transform. So some analog filter equation in the Laplace domain. And then we design the filter to convert it into the Z domain by using one of two techniques, either the impulse invariant technique or the bilinear transform. If you recall that the impulse invariant technique is basically used for transforming an analog low-pass filter to a digital low-pass filter, and the bilinear transform can transform an analog low-pass filter to either the digital low-pass or digital high-pass filter forms. So our example problem here is that we're going to be required to design a 10 Hz digital filter based on a 10 Hz 2-pole Butterworth filter using a 100 Hz sampling frequency. The equation for the analog filter is given by this here in the yellow block. Step 1 in doing this is that we need to find the inverse transform of h of s. So because this is a h of s function in a Laplace domain, we basically use partial fractions and then we reform it and so forth, and then we can look it up from the Laplace table with the general form here, and we can do comparisons, and we can see c is going to be equal to 0, d is equal to 44.4, the same thing for omega naught and a, and we can get the inverse Laplace transform here to get it back in terms of continuous time h of t. Because we have it in continuous time, step 2 means we need to get it into discretized time. So that means that we're going to have to convert from h of t to h of nt, where this capital T here represents our sampling time. We were given a sampling frequency of 100 Hz, so the sampling time is just going to be 1 divided by the sampling frequency. And we substitute that into our h of t equation to get our h of nt accordingly. Step 3 is that because now we have the h of nt function, we need to transform this into h of z using the z transform tables. We can see that h of nt is in the form a to the power n sine of bn multiplied by the unit step. And the associated transform for this in h of z is given from the Laplace table here, which we can see at this point here. So after we do the substitution and simplify it and so forth, h1 of z here is basically going to end up in this form here. At this point, this tends to be our final answer unless we ask for it in standard form. But if it's standard form, we just need to make sure that the first term in the denominator here is 1 and the rest of the terms here have some numerical value altogether. If you're analyzing the response of the filter, this is where we actually plot the graphs accordingly. So we'll plot it here to verify the performance between the original version and the scale version. Now one thing to note is that even though we have the analog response here from the original and the scale version here showing that the red plot is the analog response and our blue plot here is the digital response, we can see basically they tend to be lined up pretty similar to each other. However, when you're doing this in digital form, sometimes you may need to amplitude scale. And as such, the final version, by doing the amplitude scaling, will resolve into this form here accordingly. So this is the walkthrough, or basically the design steps taken to do the impulse invariant technique. And the MATLAB implementation of this is given by these MATLAB commands here, where basically we need the b and a coefficients here to input into the impulse invariant function, and then we'll get our result here accordingly, and we can test it with it using the FDA tool. So our next problem here is that we're going to have an h of s filter equation, and we're going to have to design for the same 10 Hz IIR filter to match the 10 Hz analog filter with a sampling frequency of 100 Hz. But in this case, we're going to be using the bilinear transform instead. So in doing the bilinear transform, the general steps is that we need to choose the appropriate analog filter And then we match the analog frequency and the digital frequency using the f of a equation here for the low pass to low pass versions. So this is for the analog low pass to a digital low pass version. We calculate for C accordingly, and then we substitute for S using the bilinear transform to get it in terms of Z. So we already have the appropriate analog filter equation. We're going to have to match the analog frequency and the digital frequency, and in this case we're going to be calculating for C. So we have our f of a equation here to match a low pass analog filter to a low pass digital filter. And we know that the analog frequency here was 10 Hz, and that the digital frequency here is equal to 2 pi fc divided by fs. We have our cutoff frequency, which is 10, our sample frequency, which is 100, so we can calculate for omega here. We can then rearrange this equation here to make C the subject of the formula and solve for C accordingly. So in this case, it will resolve to 193.3. Because we're dealing with a low pass filter, that means S is equal to C multiplied by Z minus 1 divided by Z plus 1. If it was the high pass filter version, this would be Z plus 1 divided by Z minus 1. And our analog filter equation, our analog frequency equation will map such that instead of this being f of a in this form here, it will now be f of a equal to minus C divided by 2 pi cosine of 0.5 pi. So because we're dealing with the low pass version, we'll be using this form of S here accordingly. And we substitute S here into our equation to get our H of Z. Now, for homework, I'd like for you guys to substitute and simplify this equation here and get it into the standard form. And you'll notice the steps that you need to take while doing this is that you need to make sure that there are no improper fractions either on the numerator or the denominator accordingly. So a trick would be to multiply the entire equation, numerator and denominator, by z plus 1 all squared accordingly. The final answer you should get is something in this form here. Because this is the anti-causal form, because we have positive powers of z, we need to transform this into the causal form, so that way we get it into negative powers of z here. And then to express this in standard form, we take this value here and we divide the numerator and denominator by this value accordingly. So in standard form, what we'll get is that our h of z will be in this form here as well. And this tends to be our final answer as well if the question asks if you to express h of z in standard form. If we plot the graphs to see what it looks like, is that we can see that it does a very good job of matching the analog and digital frequency responses. And one thing to note is that the bilinear transform here automatically scales the amplitude response, so there's no need for doing amplitude scaling accordingly. In MATLAB, the commands for the bilinear transform is given here, where we're going to have to know what is the B, A, f of s, and f of p coefficients accordingly in order to calculate for our bilinear transform. A of z and b of z here will basically give us our coefficients for the numerator and the denominator accordingly, and we can also test with this using the FDA tool. So this brings us to the end of our IIR filter design lecture series.